Review Lesson 2, Function Notation, Domain and Range, and Difference Quotients. Our objectives for today are identify the domain and range of a given function, so that's vocabulary, domain and range, evaluate a function at a specified value, and evaluate difference quotients for specific functions. So difference quotient is also a vocabulary term. We will actually begin our lesson by briefly considering what function notation is, and also vocabulary for today is piecewise defined function. So what is function notation? So you can have y is equal to x squared, but when you write f of x is equal to x squared, we call this function notation. So this is function notation. In function notation, you're giving a name to a function. So now our function has the name f. And this part is called the input for the function, and the whole thing here is called the output of the function. So we know that for a function, you have input values, which are elements of the domain, and you have output values, which are elements of the range. In function notation, as we said, our input is right there, and the whole thing, f of x, is our output. So if you wanted to make a table using function notation, you would write x for the input and f of x for the output. And you can see that f of x is y. It's the same as y. So both tables will have the same output values, but you just have to understand that in function notation, f of x is the output. So negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So here I have the function y is equal to x squared plus 5. If I wanted to represent that using function notation, I can give it a name, such as g. So I have g of x is equal to x squared plus 5. And of course, you can make a table of input and output values. And if you wanted to do it using function notation, your output values would be notated with g of x. And you can choose different values for the input. And then to find the output, you would just take the input. In function notation, the input is x. You'd replace x with whatever your input is and do the rule. So in this function g, the rule is to take an input, square it, and add 5. Follow the order of operations. So if the input is negative 2, negative 2 squared is 4, 4 plus 5 is 9. If the input is negative 1, negative 1 squared is 1, 1 plus 5 is 6. If the input is 0, 0 squared is 0, plus 5 is 5, and so on. And of course, because these are the same rules, you will actually have the same tables, input-output tables. But what we call this function notation. We will now take a look at an example and go over objectives 1 and 2, identify the domain and range of a given function, so we will have a chance to discuss vocabulary, and evaluate a function at a specified value. So we will take a look at number 1 here. In exercises 1 and 2, use the graphs of f and g to answer the following. We'd like to take a look at number 1 for the function f. So it says identify the domain and the range of the function f and also g, but we will focus on f. So what is the domain? The domain is the set of input values for the function. What is the range? The range is the set of output values for the function. So in part A, we're being asked, identify the domain of the function f and the domain of the function g. So the input values are the x values, and the output values are the y values. So when you look at the graph that is given for the function f, which you of course see here, you want to ask, at what x value does the graph begin? And at what x value does the graph end? So if I trace it here, you can see that the graph of f starts at x is equal to -4, and it ends at x is equal to +4. So the domain of the function f would be from -4 to +4. I wrote the domain using what we call interval notation. If you have brackets, that means -4 is included as well as 4 is also included, and it's all numbers between -4 and +4, including the endpoints. Alternatively, you can also write x is between -4 and +4, including the endpoints. Or you could even use set notation, in which you write the set containing x values such that x is between -4 and +4. So there are different ways you can write the same information. The range of f, again, the range is the set of output values for the function. It would be the possible y values for the function. So if we look at the graph of f, you can see that it starts here, where the y value is -3, and it ends here, where the y value is +5. So the range of f is from -3 to +5. You could also write y is between -3 and +5, including the endpoints. Or if you wanted to, you could use set notation and write the set of y values such that y is between -3 and +5. There are different ways you can write the answer. Now we go on to part B, and we will focus on the function f. So it says here, identify f of -2. We began this lesson by reviewing function notation. So the part that I boxed in red, f of -2, is talking about the output from the function f when the input is -2. So you want to understand exactly what I just said. And I wrote it so that you can see what we're talking about. So in function notation, this is the input, or the x value, and f of -2 is the output, or the y value. So when it says identify f of -2, it's asking you to find what the output for the function f is when the input is -2. And again, input is x and output is y. So when x is -2, what is y? So you look at the graph of f, here's -2, and you look at this point which is on the graph of f, and what you can see is that when x is -2, y is -1. So when the input is -2, the output is -1. So to answer the question, we're going to write f of -2, which is the output, is equal to -1. You can write an ordered pair. You can write -2 comma f of -2. That would be input and output. But of course, what is f of -2? F of -2 is -1. So to answer the question, this is what you would have. F of -2 is -1. Now we look at part C. It says, for what values of x is f of x equal to g of x? In other words, for what x values will the outputs from the two functions be equal? The output values are the y values. And you can see that the two functions will have the same y value where the two graphs intersect. So for what x will the y coordinates be equal? When x is equal to -1, both functions will have outputs of 0, as we can see from the graph. Part D says, estimate the solutions of f of x is equal to 2. So for what x value is the output from the function f equal to 2? That's another way you can phrase the question. And you can see that that happens here. You have this point on the graph of f where the input value is 1 for x and the output value is 2 for y. So f of 1 is equal to 2. So the solution of this equation would be x is equal to 1. Another way you can understand that is you can think of it as solving this equation. F of x is equal to 2. So that's y is equal to 2, whose graph is a horizontal line. And where does the graph of f intersect the horizontal line? At x is equal to 1. We can briefly take a look at part E here. Estimate the solutions of g of x is equal to 0. So here's the graph of g. And for what input values will the output values be equal to 0? The output values are the y values, and you can see that the graph of g has these 3 points with y coordinates of 0. So for part E, you will say, estimate the solutions of g is equal to 0. That happens when x is -1, when x is +1, and when x is +2. Those are the 3 input values for the function g that will result in output values of 0. Now we will look at another example for objective 1. Identify the domain and range of a given function. Number 18, find the domain and range of the function. In the previous example that we looked at, we were given the graph of a function f, and we looked at the graph to find the domain and range. Here we're not given the graph of g, we're given the algebraic rule for the function g, and we want to find the domain and range. You could try to graph it using a graphing calculator or Desmos and try to do it the way we did number 1. However, you could also analyze this analytically. What is the domain? The domain is the set of possible input values for the function. So what value of x is not possible as an input value? You can't have x be equal to 1, because if x is 1, we will have division by 0, which is undefined. So this is how you write the domain for the function g. You can write the domain for g in words like I just did now, all real numbers except 1. You could also write it using interval notation. To help you understand how to represent this information using interval notation, I will draw a number line. All real numbers except 1. So 1 is not included, but all other real numbers are. So how can you represent this using interval notation? You're going to write from -infinity all the way to 1, not including 1, together with union from 1 to +infinity, not including 1. This is read union, and that means we consider both intervals when we think about the domain. When we think about the range, we're thinking about the set of possible output values or y values from this function. you will notice that if x is greater than positive 1, then x minus 1 will be a positive number. For example, if x is 2, 2 minus 1 would be positive 1. If x is 11, 11 minus 1 would be 10. On the other hand, if x is less than 1, x minus 1 would be a negative number. The numerator is always 2, so if you divide the numerator by a positive number, you will get a positive number. If you divide the positive numerator by a negative denominator, you'll get a negative output value. So the output values can be both positive and negative, but the one output value we cannot have is 0, because the only way we can have a fraction that's equal to 0 is if the numerator is 0. The numerator is always 2. So we can't have 0, but we can have all other possible output values except for 0. And in fact, the output values can be extremely large. If you divide 2 by a very small positive number, you'll get an extremely large output value. Or it could be negative with a magnitude that's very large. So for example, if you divide 2 by a very small negative number, you'll get a negative output value with a large magnitude. So for that reason, the range is all real numbers except 0. You can write that in words, or you can write that using interval notation. We will now take a look at some examples for Objective 2, evaluating a function at a specified value. Here we have number 3, evaluate if possible the function at the given values of the independent variable. Simplify the results. So our function is written in function notation. F of x is equal to 2 times the input minus 3. Notice that I read the x as 2 times the input minus 3. So in part A, the input is 0. So the function says you should do 2 times the input minus 3. So you'll have 2 times 0 minus 3, which is 0 minus 3, or negative 3. In part B, the input is b. So you're going to have 2 times the input minus 3, and this would be the output in part C. The input is b, so you have 2 times the input minus 3. Number 27, evaluate the function as indicated, determine its domain and range. Number 27 is called a piecewise defined function, which is one of our vocabulary terms. And it is called a piecewise defined function because there are different rules or different pieces of the function depending on the input value that is given to the function. So if the input value is less than 1, this is the rule for the function. If the input value is greater than or equal to 1, you use this other rule for the function. And the two rules together make up the function for all possible values from the domain of the function. So let's think about the domain first. What is the domain of the function? Well, you can have an input that's less than 1, or you can have an input that's greater than or equal to 1. So basically, you can have any input. But depending on the input, you will either use the first rule or the second rule. But the domain is all real numbers. So we will take a look at part A, evaluate the function as indicated. So you have to understand function notation. So we know the input for our function is negative 3. And you're going to compare that to how we divide the domain. We divide the domain as you see here. If the input is less than 1, and that's the case for part A, we're going to use the first rule. So f of negative 3 is given by the first rule, the absolute value of the input plus 1. The absolute value of negative 3 is positive 3. 3 plus 1 is 4. How do you do part D? What is the input? The input is b squared plus 1. We don't know what b is, but we know that whatever b is, we will square it and add 1. When you square any value, the square of any number is non-negative. The least it could be is 0. So the least b squared plus 1 can be is 0 plus 1, or 1. So b squared plus 1, the input here will be greater than or equal to 1, and for that reason, you should use the second rule from the piecewise defined function for the input b squared plus 1. So what do you need to do? If you look at the second rule, it says whatever the input is, multiply it by -1, and then add 1. So the input is b squared plus 1. So I'm going to take b squared plus 1, multiply it by -1, and then add 1. So when I distribute the negative sign, I will get negative b squared minus 1 plus 1, which would just be negative b squared. To think about the range, you can think about the possible output values from each piece of our piecewise defined function. When we look at the first piece, we know that the absolute value of x will be 0 or greater for any x, and then we're adding 1 to it. So the absolute value of x plus 1 will be greater than or equal to 1 for any x. And of course, for all x that are less than 1 as well, because this is true for any x. But you also need to consider that x is less than 1, which would include values like x is equal to 0. And when you have x is equal to 0, the absolute value of 0 is 0, 0 plus 1 is 1. Actually, the easiest way to find the range for this function is to graph this piecewise defined function. To graph the piecewise defined function, we can start by graphing the second rule, which has the form y is equal to mx plus b. We have y is equal to negative 1x plus 1. So the y-intercept is 1 and the slope is negative 1. So here's the graph that we have for the second piece. However, I need to erase a part of it because we would only have this graph for x values that are greater than or equal to positive 1. So the graph would actually start here at x is equal to 1 and continue as I have shown. So now you need to graph the other piece, and this is for x less than or equal to 1. And if you'd like, you can make a quick table. Choose values of x that are less than 1. So 1 is not included, but I will have it there. I'll just sort of put an open circle there because 1 is not included. And then you're going to have values that are less than 1. So the absolute value of 1 is 1. 1 plus 1 is 2. The absolute value of 0 is 0. 0 plus 1 is 1. The absolute value of negative 1 is 1. 1 plus 1 is 2. The absolute value of negative 2 is 2. 2 plus 1 is 3. So if I plot these points, I have 1, 2, which is right here, and then I have 0, 1, and then I have negative 1, 2, and then I have negative 2, 3. So here's the graph that I have. And we know that at x is equal to 1, we're going to have an open circle because I only use this rule for x values that are less than 1. So we have an open circle here, and here's the graph. So when you look at the graph, you can see what the range is. The y values are from negative infinity all the way to 0 for y, including 0, and then from positive 1, which you see here for y, all the way to infinity because of the left side of the red branch of the graph. So that's the range. So today we reviewed function notation, domain, range, and piecewise defined function. We looked at the first two objectives: identify the domain and range of a given function, either from a graph or from a function rule, and evaluate a function at a specified value. We're going to take a look at objective 3 later. We won't include it today, but we will come back to this later. Evaluate difference quotients for specific functions. We're going to postpone that, and of course that vocabulary term will be postponed as well.